So what we're going to look at today is part-whole ratios. We're going to look at some situations where we can add the quantities in a ratio together. So today's I can create tape diagrams to help me reason about problems involving ratio and a total amount. I can also solve problems when I know a ratio and the total amount. All right, let's dig in. All right, so let's, before we dig into the rest of it, let's do a little true false, making sure that we understand multiplying and with unit fractions, because something that sometimes gets a little tricky. So if we look at this first one here, we have 1/5 times 45. Is that going to be 45/5? Is that true? Yeah, it is, because remember that this, when you talk about multiplying a whole number times a fraction, you're going to make that whole number over 1 to make it a fraction. 1 times 45 is 45. 5 times 1 is 5. What about here? Can we make this 1/5 times 20? Is that going to be the same as 1/4 times 24? No, it's not. We're multiplying by completely different things. So this one is false. What about this one? We've got 42 times 1/6 equaling 1/6 times 42. Are those equal? Yeah, they are. They're absolutely equal because it's just the same thing, and the commutative property tells us that each one of those, as long as we're keeping everything the same, we're just shifting around, that works just fine. What about 486 times 1/12 being the same as 480 twelfths plus 6 twelfths? Well, doesn't that just what this is splitting up? If you split this into 480 and 6, because you would add those together, and you take the 1/12 times each, wouldn't that give you that? Sure would. So part of the reason why we were looking at these for the true-false piece of it is to help us remember that when you're talking about multiplication, numbers can move around certain ways, but that doesn't mean that you can just wholesale swap digits around. You have to do them logically. All right, and that's kind of what we're talking about with today's lesson, looking at knowing parts of a ratio and knowing, then finding the whole part. Okay, so to kind of help us visualize this, I've got 3 yellow cubes and 1 blue. Okay, and this would be, let's say this is the same portion as what we talked about with colors before, to make green. Okay. Well, if we said that each one of these was 1 milliliter, how much total would we make? Yeah, we would make 4 milliliters, because if each one of these is worth 1 milliliter and we use 3 yellow and 1 blue milliliter all together, that gives us 4 total milliliters. What about if each cube is 2 milliliters? How many milliliters of paint do we make that way? Well, let's see. I'd have 2, 4, 6, 8. 8 milliliters. Why is that? Well, each one of those being worth 2 would give us a total of 8 at the end. Is there another way that I could do this to show 2 milliliters of blue and 6 milliliters of yellow? Well, I could get 6 yellow and a total of 6 yellow and a total of 2 blue if I wanted to do it that way. And then if I did that, though, how would that relate to batches? Why would that be, how could that relate to the term batches? Well, if the original formula was 3 yellow to 1 blue, then by going by that, if we use 2 milliliters of blue and 6 milliliters of yellow, then we're making another batch. So we'd have 2 batches. It's kind of like recipes. If you want to have double the servings, you have to double all the ingredients. If you want to have double the batches, you'd have to double each part. So each of those does become a batch in its own way. So let's think about this a little further. So if I have to make purple, well, a sort of purple, I think it'd be more maroon because it looks like we have more red than blue. To make this particular shade of whatever color we make with this, I have, it looks like 5 units of red to 3 units of blue. So if we had each one of these worth 1, that would make a total of 8 whatever units we were using. So let's say that these are milliliters. So if each one of these is milliliters and we had that like that, we would have 8 total milliliters. Well, we can see that we have each one of these is worth 10 milliliters. So altogether we would have 80 milliliters, right? Now, how do I know that? Well, I've got my 5:3 ratio. I know that each one of these is 10 milliliters. And then it's just a simple thing of going, knowing that altogether in one batch you get 8 milliliters. And if you've got each of those parts at 10, you're just going 10 times as much. So it's kind of looking at the same sort of thing we talked about before with when we're talking about converting ratios and seeing how much we have in different ways and changing those ratios, like as in recipes and such. But this is, thinking about that total and then thinking about how many you've got for each of the parts and using that to inform what the grand total is of the entire thing when you put it together. Okay, so this is from earlier. We have a 3-to-1 ratio. What if we had each one of these units as 5 milliliters? How many total milliliters do we have? Well, if each one of those is 5, then we end up with 20 milliliters, right? Because we have 4 parts that come together total to make the total. Now, when we talked about it originally, when we looked at it the other day, we had 15 yellow to 5 blue. Well, it still ends up working out the same way here. So it's just really a matter of understanding that each of those parts on their own come together to make the whole color green. And in this case, we have a total of 20 milliliters when we get finished. So let's get down this definition real quick. So a tape diagram is a group of rectangles put together to represent the relationship between quantities. So in other words, in this example here, we had 30 gallons of yellow paint and 50 gallons of blue paint. Together we make 80 gallons of green paint. Well, a type of green. It would be more blue than it would be yellow. But the point is that these parts coming together give you what the grand total is. And we could change these depending on the situation, couldn't we? So like if we used 5 instead of 10, we'd have 40. If we used 15 total yellow, that would be the 5 yellow that we talked about, 25 of the blue. Again, it's one of those things where you can change these to help you be able to answer whatever question you need them for. All right, let's put some of these into work. So let's try this first one here. Student ratio of students wearing sneakers to those wearing boots is 5:6. If there are 33 students in the class, all of them wearing boots or sneakers, how many are wearing sneakers? All right, so you should have worked it out. You may have needed to draw something for it. Let me add that piece in here real quick. So I know that altogether I have 33, right? Well, I have 5 to 6. Together, how much do those make? Yeah, 11. So what I have to do is figure out how much each of these parts have to be so I can figure this out. Well, if I have a total of 11, each of these parts is 3, isn't it? Fast forward. Poof. So I have 5 of these, which gives me 15. And I have 6 of the 3s, which gets me 18. Together, those make 33. Now, you may not use tape diagrams forever, but they can be a great way to organize your thinking when you get stuck, especially with ratios. Okay, let's go a little bit tougher. 3 parts oil with 2 parts soy sauce, 1 part orange juice. You need 42 cups. How do you need to put this together? What's it going to look like? Okay, well, to get your answer, let me draw my parts. So I got my oil, I got my soy sauce, and I got my orange juice. So these 3 together these 3 ingredients together make one whole marinade, which I have 3, 2, and 1. Well, that gives me a total of 6, right? So I have to take 6 as a total. 6 parts together make the total. How many cups or how much of each ingredient will I need? So I need to take this 42, divide it by the 6, which should give me 7 for each. And then if I know that each of those is 7 when I break this apart, then it's pretty simple to figure it out. So the oil, I need 21 cups. I need 14 cups of the soy sauce. And the orange juice, I'm going to just need 7 cups of it. Again, these tape diagrams can help you organize your thinking a little bit better. It's not something you'll necessarily always need to use, but it can certainly help when you're stuck. So real quick, let's kind of think about it. So these doing the ratios here were a little different than what we did before, right? Big difference here between these and the other ones were we had to figure out what the whole recipe made, for a term. So what the whole recipe made, and then use that, the ratios to help us break it down to figure out how much we need of each things. Tape diagrams helped us to organize our parts so that we could see that all together in one batch, you would have so much, and then knowing how much you had in one batch, you could figure out from the total how much you needed of each. Changing the value of each part of the tape diagram ended up having a multiple effect on the rest of it, didn't it? So if you changed, instead of everything being 1 milliliter, you changed everything to 5 milliliters. Well, now you made 5 times as much as you did originally. Okay. Again, tape diagram, just like everything else in math, it's a tool, and it's certainly a tool that you can use down the line as you choose, but within the particular assignment, it is a great way to help you understand and answer questions. All right, so you are all set for this particular lesson.